So hi everyone, in this last video of this unit, we are going to use everything that we proved in the previous video, and also maybe with the motivation and intuition that we got from previous videos to prove that the polynomials that we are looking at, namely characteristic polynomials of A plus PB P transpose, where you go over all permutation P in Sn, that forms this set of polynomials is nice enough so that you can say that the average polynomial, say according to the uniform distribution, that's what we are looking at, the max root of that actually bounds the max root of one of these polynomials. And for that, we really need to understand the permutation group in the context of real-rooted polynomials. And we are going to use all the 6 lemmas that we saw, and we need some very nice idea. I think it's a really cool video. So let's get right to it. So first of all, I want to give the definition of an interlacing family of polynomials. So that's kind of going to be an abstraction of the fact that the polynomials that we are looking at are in such a configuration that you can connect them in pairs and then connect them in pairs in such a way that on the segments connecting them, you can keep connecting them in pairs and so forth until you reach the polynomial, which is the expectation of them, in such a way that none of these segments never touch the double root manifold. But we are going to state it in kind of more abstract terms, as you'll see. It will enable us to focus on what we need. So we are looking at a tree T. It's going to be the full rooted binary tree. So every vertex has a left and a right sun, by the way. So it's a kind of a planar graph. All trees are planar, but it's a planar in the sense that there is a left sun and a right sun. Also, we distinguish between the two. And every non-leaf has a left sun and right sun. And in fact, all the leaves will be on the same level. Okay. So I never know if it's called full or complete. So it's that one. But that's a tree. And the point is that for every node in the tree, to every node in the tree, are going to associate a polynomial, a real value, a real polynomial with real coefficients. It's going to also have real roots, but not now. So it's a polynomial over R. And PT will denote just the set of all polynomials that you see in the tree. Okay. Now the collection T and the polynomials attached to T, PT, with the attachment, is called an interlacing family if three conditions are met. So first of all, you want that every polynomial there, for every vertex, you want it to be monic, and you want it to be real-rooted. So it's not only a polynomial of real coefficient, but on top of that, it should be real-rooted. And moreover, the degrees of all polynomials in the family is the same, some n. Okay, so that's what we have here. So that's one thing. Second thing is the following. You want that if you look at an internal node, namely a node which is not a leaf, so it has two suns, U and V, and again, it's a left sun and a right sun, then you want that there will be some relation between the polynomial of V and the two polynomials of its two suns. So you want that there will be some alpha in 0, 1. That alpha may vary with different vertices, but for every V there is some alpha, such that PV of X is just a convex combination according to alpha of the polynomials of its two children. Okay, so you can kind of see here you have the segment connecting PU and PW, and PV should in that language it should lies on that segment. And the third thing that will enable us to talk about the max root and so forth. So any two siblings, namely UW, which have a common parent, immediate parent, so their two polynomials should have a common interlacing. Right, so PU and PW, from property 2, you want that the PV lies in between them, and in property 3, what we want is that these two polynomials have a common interlacing. It has nothing to do with PV, by the way, just a common interlacing, and that common interlacing is not, we don't have any notation for it. You just want that polynomial to exist. And if you recall, saying that PU and PW have a common interlacing is saying that the interval connecting them doesn't touch the double root manifold, which was crucial for saying that the max root of everything in between is bounded by the max root in the segment is bounded by the max root of one of them. Okay, so these are the three conditions. So all polynomials in the tree should be real-rooted, same degree, monic. Monic is, you can generalize, but monic, just for simplicity. And then you want that the relation between the polynomials is such that two siblings, the polynomials of two siblings is such that their parent, the polynomial of their parent lies in the segment connecting them, and two siblings, their polynomial has also a common interlacing. Now, it's going to be the other way for us. We are going to start with some polynomials, the polynomials that we are looking at, the characteristic of A plus PBP transpose over all P's, and we will want to construct an interlacing family, namely a tree that has these properties that we talked about. And so in order to do that, let me introduce another definition, and the lemma that follows will tell you why we care about these things. So a set of polynomials, and again, you should think of our set of polynomials, which is just a set. It has no, we currently don't have understanding of its structure. So it is said to form an interlacing family if there exists an interlacing family, there exists some tree with the properties that we talked about, such that for every leaf, the polynomial attached to that leaf is from our set. Okay, so you start with a bunch of polynomials that you care about, and this definition tells you that this family of polynomials forms an interlacing family if there is some tree. There could be several, but if there is some tree with the properties, with polynomials satisfying the properties that we discussed, and the relation of that tree to our polynomials that we are starting with is that the polynomials on the leaves are from our family. They can repeat. I mean, one polynomial from our family can appear, and in our case, it will appear many times in many leaves. But what's crucial is that the leaves will contain only polynomials from our family. In such case, we are saying that the polynomial set that we have form an interlacing family. Okay. So why do we care about that? Well, that's because of the following lemma, which is a one-liner given what we did in the previous video. It says the following. It says, say you have a set of polynomials, all of them of the same degree n, which forms an interlacing family. Okay. And let T be D or a corresponding tree and having root R. Then what I'm claiming here is that for every j, we care about j equals 1 or 2, but for every j between 1 and n is the degree of the polynomial, there exists some I in M, like a polynomial in our family that we started with, such that the jth largest root of pi is bounded from above by the jth largest root of the root of the tree, the polynomial associated with the root of the tree. All right, so this lemma tells you that if you have a set of polynomials and it forms an interlacing family, it has some structure, then if you want to bound, say, the max root, if you are bound on the max root of the polynomial that appears in the root of the tree, and of course you want to choose that polynomial carefully, but you want to construct the tree such that that root will be what the expectation, or according to some distribution that you have. In our case, it's uniform. Then that lemma tells us that a bound on the, say, largest root of the expected characteristic polynomial, something that appears in the root, yields an upper bound on the largest root of one of the polynomials in the family, which is exactly kind of what we want to have. So let's prove the lemma. Again, it's essentially a one-liner. So we are going to use a lemma F, and I just wanted to remind you of what this is lemma F. And lemma f tells you that if you have two real-rooted polynomials, p1 and p2, and they have a common interlacing, so this means, right, that the segment connecting them doesn't cause a loop manifold, then either for any j, either p1 or p2 is such that lambda j of that a particular polynomial is bounded by lambda j of a convex combination of them. So then more precisely, given a convex combination, given alpha, and when you look at alpha p1 plus 1 minus alpha p2, you can bound either p1 or p2 depending on alpha and j. You can bound the jth largest polynomial of one of these polynomials by the lambda j of the convex combination of them. Okay, and I also want to remind you property 2 and 3 that we just had in the definition of the tree that we are looking at. So right, if you have, let's start at the root. If this is the root and this is u, and maybe here you have some other vertex v, then we know two things. Property 2 tells us that the polynomial associated with the root is a convex combination of the polynomials corresponding to u and v. That's this thing. And property 3 tells us that the polynomial corresponding to u and v have a common interlacing. I should say have a common interlacing. Okay. Now, because they have a common interlacing, and because PR is a convex combination, lemma f immediately implies that lambda j of either u or v is bounded by lambda j of PR. Right? Because PR is of this form, and they have a common interlacing. And so, you know, that for every alpha, I don't know what alpha, but for every alpha and j, one of u or v is kind of better than R, namely the corresponding corresponding root that you care about, the jth largest root, is bounded by, say, of u, is bounded by the jth largest root of p of R. Okay, and you know, once you have that, you can just repeat as you go down in the tree, right? By the same argument, if you look now at u and you look at its two sons, then again, pu is a convex combination of the polynomials of its two sons, which have a common interlacing, and so this means that one of its two sons has a bound on lambda j, which is better than the bound that we have on lambda j of u, which in turn is better than the bound that we have on lambda j of pr. And you can go all the way to the leaves like that. And once you reach a leaf, you know that lambda j of that leaf is smaller or equal than lambda j of the root. So it's essentially a one-liner, but with induction. So the kind of double picture you should have in mind is that, you know, maybe this is the tree that you have, but geometrically what happens is this thing. So say you have polynomials p1, p2, p3, and p4, which form an interlacing family. And so here is a tree that describes the interlacing family. So here you have a polynomial pu, pv, and pr. And you know that, right, p1 and p2 have a common interlacing, and also p3 and p4, and also pu and pv. And you also know that pu is a convex combination of p1 and p2, and pv is a convex combination of p3 and p4. And PR is a convex combination of pu and pv. Right? That's what you know. And what we just showed is, that's okay. So that's that. And on the geometrical picture, geometrical side, when we look at the coefficient space, you know, the polynomials are sitting as points. By the way, I should say I could have used more. P2 could appear several times as a leaf, but I just wanted to keep it simple as an example here, or an illustration. So right here, P1, P2, P3, and P4 are points. And the fact, and this yellow line curve is the kind of the manifold of the double root manifold. So saying that P1 and P2 have a common interlacing, property 3 tells us that this line doesn't cross, you don't have something like that. It doesn't cross the manifold. And also P3 and P4 don't cross the line here doesn't cross the manifold, the segment. And saying that by property 2, saying that PU is a convex combination of P1 and P2 is really just mean that PU sits in that segment. And same as for PV. And again, saying that PU and PV have a common interlacing says that now this line, right, doesn't cross the manifold. And then saying that PR is a convex combination of PU and P3 says that it just sits somewhere here. So the tree kind of abstracts the fact that you can connect the original polynomials thought of as points in Rd plus 1 or Rn plus 1 in such a way that you can find convex combination, that you can find point on the segments which can also be connected and so forth. So you cannot do that maybe, and you cannot maybe maybe in this case you kind of can, I don't know. So maybe you cannot immediately connect P1, P2, P3, and P4 to PR, but you can do it in steps like that. Okay, and so the main theorem that we are proving here, which will imply the main theorem of the unit, is that for any n by n real symmetric matrices A and B, the set of polynomials that we care about, namely the characteristic polynomials of A plus PB, P transpose, when you go over all P in Sn, this set actually does form an interlacing family. And not only that, I mean, in the lemma that we want to invoke, the promise was that if you know something about the root of the tree, the polynomial attached to the root of the tree, then you know something about one of the leaves. So you don't want just these polynomials to have a common interlacing. What you want also is that to the root of the tree, the polynomial that is attached is the polynomial that you know how to bound its max root. So indeed, to that set of polynomials, there is an interlacing family, namely a tree and a bunch of polynomials attached to the vertices, such that the P of the root is exactly the expected, according to the uniform distribution characteristic polynomial of A plus PB P transpose. Okay, so that's a strong theorem. It tells us in particular what I owed you for quite some time, namely that this polynomial is at all real rooted. I mean, it's not obvious that it's real rooted, and by me saying that this set of polynomials form an interlacing family whose root, the polynomial whose root is that polynomial, that immediately implies, because by the definition of interlacing family, all polynomials are real-rooted, immediately implies that also this polynomial is real-rooted. And I should remark that the original proof, if I'm not mistaken, was different. For the proof of the real-rootedness of this polynomial, you can do it in several ways. You can either go to like a multivariate version of what we are doing, which it's actually very interesting. I inserted a paper that relates to that in the projects for the end of the semester. Or you can, unless I'm mistaken, also understand this polynomial, but maybe I'm slightly being inaccurate here, as the matching polynomial. And it's some polynomial which is known to be real-rooted. But maybe there is a variant to that. Okay, so anyhow, once we prove theorem 2, we actually prove that this polynomial is real-rooted. And it immediately also implies theorem 1, right? Because what is theorem 1? Oh, it's a long unit. So theorem 1 tells you that the max root of this polynomial, namely you remove the obvious root, is a bound on the max root of one of the polynomials that participate in the expectation. And if we prove that these polynomials as a set forms an interlacing family, then by the lemma, the max root of one of the leaves is upper bounded by the max root of the root of the tree. Okay, so our goal is now to prove theorem 2. So we somehow need to construct this tree to kind of break down the permutations in such a way. So we need some notation. So for a swap permutation, again, a swap permutation, just kind of an ij permutations, flipping I and j, we denote the corresponding matrix by gamma ij. Right, so gamma ij of ei is ej, and of ej is ei, and gamma ij of ek is just ek for every k that's not I and j. And so that's a swap permutation. We are going to consider random swaps, namely, given I, j, and alpha, we are going to consider a distribution which with probability alpha will do nothing, but with probability 1 minus alpha will swap I and j. And this is the corresponding matrix, right? And so the swap, I mean, that's a matrix, and it kind of encodes that what I said. And the swaps lemma tells us, it's kind of one of these questions you can ask at some high-tech interview. It's an easy question, an easy lemma. I think it's definitely a somewhat hard question for an interview, but it's an easy lemma for like math. So the swaps lemma tells you that you can break down a uniformly random permutation to a product of random swaps. Okay, so if you want to generate the uniform to generate the uniform distribution over permutations, and P will be the corresponding matrix, then you can write it as a product of T1 up to Tn. Capital N will depend on the dimension little n. It's going to be exponential little n, as we'll see, but never mind. And each of these Ti's is a random swap. It's something that looks like that. Okay. So let me sketch the proof. So it's kind of by induction. So what you should do is the following. So the first thing you should do, I mean, there are several ways of doing that, but one thing, this is one way. The fourth thing you should do is you can just permute 1 to n minus 1. Namely, kind of by induction, you can write mn minus 1 as a product of some number of swaps, capital N of n minus 1 swaps. And that leaves n, sits there by itself, and all the rest are kind of completely permuted nicely and uniformly. And then, what you should do, you should kind of keep this element sitting with itself with probability 1 over n, because that's a probability that will permute to itself. So that's here. And then with the remaining probability, you should just replace it with, any one of the elements, because they are completely permuted. So maybe swap it with 1. Right, but now okay, so now what you need to do is to kind of re-permute it again, because you left someone alone like that. It's not a random permutation, doesn't have someone sitting alone for probability 1. So you re-permute again 1 up to n minus 1, and you get the uniform distribution. Okay, so let's see how it works. So for example, M1 is just I, and you have one element, just do nothing, it's fine. M2, you don't need this lemma. You know that with probability 1/2 you should have I, and with probability 1/2 you should have a gamma 1, 2. That's like T1. That's the only swap that you have. It's a random swap. But it also kind of agrees with this, of course, right? Because if you put an identity here coming from the one case, and you put n equals 2 here, then you get M2. Right? So M3, let me just clean it a little bit. M3, so I just use I'm just kind of using this formula, right? So this is M2 appearing twice as it is required here. And then I'm putting here 1/3, because n is 3, 1/3 I plus 2/3 swapping 1 and 3. And you can look at it, you can open it up a little bit, and you can convince yourself that that's actually uniform over the permutation group of 3 elements, like over the 6 elements of the permutation group. And you can easily see that capital N of little n, namely the number of random swaps that you have, is doubled when you move from little n to little n minus 1, because you have 2 of those. And you add one more random swap. So all in all, taking into account that M1 has no random swaps, the number of random swaps that participate is exponential in n, 2 to the n minus 1 minus 1, if you want. Now, if you look at it, you may get confused, or maybe I'm just going to confuse you now, because you may have expected to see something larger than n factorial, because you say, well, I need all n factorial options, but this has nothing to do with it. This is the number of random swaps. If you open up all of these, you get 2 to the n minus 1 permutations, and that's more than enough to accommodate for the n factorial permutations that you expect to see. Okay, so with these swaps, let's prove theorem 2. We call theorem 2 requires us to construct an interlacing family to the set of polynomials that we care about, where the root has a polynomial which is the expected characteristic polynomial according to the uniform distribution, which in the last video of the course, which is the next one, sad and happy, we are going to bound its max root, or second largest max root. So the proof of theorem 2 is as follows. So instead of talking about tree of polynomials, let's talk about tree of distributions, and then the polynomials will kind of be induced by these distributions, and it's actually nicer to work with the distributions rather than the polynomials, because that's what we're actually doing here. So let's see. So we are going to construct a tree T, okay, of distributions, namely to every node we are going to associate a distribution, which is denoted by nu v for every v, and the polynomial that is induced by that particular distribution, nu v, is this thing. So PV of x is, you sample a permutation according, so in nu v is a distribution of the permutations in Sn. So you sample sample P according to nu v, and then you look at the expected characteristic polynomial according to that distribution. Okay, so hopefully at the root, nu root will be uniform. Okay. So that's actually not hopefully, that's number 3. So let me start with number 1. So the first thing is that for every leaf, the distribution is going to be constant. Like probability 1 is going to be kind of fixed on one particular permutation that depends on the vertex that we are looking at. Okay, so the distributions at the leaves are going to be the least random, constant, and in point 3, as I kind of hinted, the distribution at the root is the most random, it's uniform. And there is a certain relation between the distribution of two siblings. So let's say we're looking at an internal node, V, and it has left sign U and right sign W. Then the distribution that will correspond to U, W, and V are related in the following way. So first of all, there is a slight inaccuracy here. So the first thing, maybe actually start with this. The first thing is that the distribution of the parent V is some convex combination of the distributions of the two. Okay, so you can think, probability alpha V, some number between 0 and 1, I sample according to the distribution of U, and otherwise I sample according to distribution W. That's what I mean by this notation. And the relation between the two distributions of these two siblings, regardless of the parent, is that, whatever the left distribution is, whatever is the distribution of U, in order to sample from W, you just sample from U, right? So you get a permutation, and then you multiply it by some swap, gamma, right? And that swap, and also alpha, depends, of course, on V. Okay, so for every V, the convex combination, how much weight you put to U and W is different, and also the swaps are different. For every V, you get a different swap. But the general kind of template is this. This is the relation between the distribution of two siblings and the parent. So we are going to construct a tree like that. Okay, that's just the game plan. Maybe I should repeat. So every leaf has a distribution which is constant. Namely, there is a fixed Q there that always been sampled. In particular, the polynomial that is associated with a leaf is not an expectation, it's just a characteristic polynomial of some symmetric matrix. and keep erasing things. And the root has a uniform distribution, which means that the polynomial there is the polynomial that we will argue about. We know how to argue about using the R transform theorem and the quadrature. And then the second point here relates the distributions kind of locally in a way that would enable us to say something about the corresponding polynomials. Okay, so now the construction of the tree is going to be from the root downwards, and the proof is going to be that all of these properties are met, will be from the leaves upward. But let's start with the construction. So let's use the notation from the swaps lemma, and the swaps lemma told us that mn, for any little n, you can, maybe I'll just remind ourselves and myself also. So it tells us that for every little n, there is some matrix which I called P here, but let me call it Mn in this case. So that, I mean, P is a good name, but I want to extend it. I want some index. So Mn is the product of random swaps that kind of gives you back the uniform distribution over a permutation. And we are going to take this T1 up to T capital N, right? We fix little n, so capital N is fixed, it's 2 to the n minus 1 minus 1. And now for every k in capital N, we look at kind of the prefix of the T1 up to 2k random swaps that we have. Okay, so M of capital N is just uniform over Sn. So now let's try to start and construct the distributions, and we will see that we kind of get stuck, and we'll figure out a way of solving it. So M capital N is M capital N minus 1 times T of N, right? That's just the way we defined M capital N and M capital N minus 1. And T of N is a random swap, right? So I can write it as some alpha n times I plus some 1 minus alpha n times gamma n, where alpha n is a number between 0 and 1. And gamma n is just a shorthand for some gamma, I n, j n. So gamma n is a random swap, and I kind of hide which indices I'm swapping and just writing gamma n. So open this up, you see that you get alpha n m n minus 1 plus 1 minus alpha n m n minus 1 gamma n. So this is here. And looking at it, it suggests a way of attaching a distribution to the left sum and right sum of the root. And again, we start at the root and then we'll go on. So you look at this thing, and when you have the properties that we want in mind, then you just say, well, I should attach the distribution mn minus 1 to the left sum. That's here. And mn minus 1 times gamma n to the right sum. And then I have everything I want, right? I mean, I want two things. I want this thing to be a convex combination of these two, and that's kind of by design. That's what we did here. And secondly, I want that this distribution is obtained, or actually maybe this distribution is obtained by that one from the left hand by multiplying by some swap, and here it is. Good, so no problems here. The problem is how to continue. Okay. So let's say we want to continue, right? So here is a second level of the tree. So if you look at mn minus 1, actually there is no problem. You can do the same thing. You can take mn minus 2 and put it at the left sum of that particular vertex, and mn minus 2 times gamma n minus 1, put it at the right sum, and for the same by the same argument, this is a convex, the distribution of that is a convex combination of these two, and also kind of obviously, indeed, the right sum's distribution is the left sum times some gamma n minus 1 this time, times swap, so that's good. But when you move to the right sum, you run into trouble. Okay, that we will fix, but let me just say that explicitly. So mn minus 1 times gamma n, I mean, you have this gamma n there. So mn minus 1 times gamma n, I mean, you want to have this gamma n there because you want the relation between the left and right sum. But now, as a root to the subtree, gamma n is going to annoy us. So we need to somehow remove it. and let me show you how, or before, let me show you what's the problem. So mn minus 1 times gamma n is, well, mn minus 2 times tn minus 1. That's just this thing, like we used here, essentially, times tn minus 1 times gamma n. And then, what is tn minus 1? So it's a random swap. So it's some number times I plus 1 minus that number times gamma n minus 1. And you still carry on this gamma n. And if you want, you can put the gamma n inside. So we get, mn minus 2. And then you have, a complex combination between gamma n and gamma n minus 1 gamma n. So you might say, maybe I should put, mn minus 2 gamma n on the left side, and mn, so this is this thing, this thing, and mn minus 2 times gamma n minus 1 times gamma n on the right side. So, that's not great for two reasons. One is that the left side is no longer, the right side is no longer obtained by the left side multiplied by from the right by some swap, because this new swap actually appears kind of in the middle. And secondly, this, if you say, okay, maybe, maybe consider this thing as a whole, sorry, but this thing is not a swap. If you compose two swaps, you can get a length-free cycle, right? 1, 2, 2, 3. Well, actually, that's fine. But you can get a length-free cycle. So there are two problems, but actually you can solve both of them together. So let me show you how. So in the previous page, we started to kind of explain this. That's what was written here. Okay. And we got up to this point. And now the idea is to do the following. The idea is to indeed take gamma n, to push it or to pull it from the right. So gamma n is going to be an I here, which is good. You want an I, and then here you pull the gamma n, so you have to put the gamma n inverse, which by the way is gamma n because it's an evolution, but let's just remind ourselves it's the inverse of gamma n. So you get this expression. And the point is that now we are fine because this is a swap. Right? If you have a swap and you conjugate it by a swap, you're going to get a swap. If you have a swap and you multiply it by a swap, you're not going to get a swap, generally. But when you conjugate it, you will. Because this is just, conjugating is just name changing. So you're just name changing, any permutation will do, just name changing a swap, so that will become a swap. Right? Good. Okay, so why is this good for? Because now we have, a swap, first of all, here. It's maybe kind of more complicatedly kind of described, but it's a swap. And we are almost happy with that. The only annoying thing you will see in the recursion, as will be in a second, but annoying thing is that you have this gamma n here. Gamma n is a fixed permutation. It's not a random swap. It's not a t, it's a gamma. But if you want to continue on, then you want always the random swap to be on the right. So you can open it up to I plus gamma and work your way through. Now if you're going to open, tn minus 2, gamma n will stay on the right and will cause a trouble. So what you want to do is kind of commute gamma n all the way to the left, but of course they not commute. Mn minus 2 and gamma n not commute. Nonetheless, you can do the following. So what is Mn minus 2? Mn minus 2 is this thing, just the product of the Tn's, Ti's. And now you can introduce this gamma n inverse between gamma Tn minus 3 and Tn minus 2. And once you do that and bracket things differently so that you look at that, then that is a swap for the same reason that I was talking about before. And now you get a new swap, which you can call Tn minus 2 hat. It's not Tn minus 2 anymore, it's Tn minus 2 conjugated with gamma n. And the cool thing, so it was a swap, it's still a swap, so that's good. And the cool thing is that gamma n moved one to the left. Right? First it was here, now it's kind of here. And you can just continue doing that every time you conjugate the t to get some t hat version. And at the end of the day, you'll get gamma n times m hat n minus 1, which is the product of hats of the TIs. And that's good because, that's a fixed swap, and these are n minus 2, so one less random swaps that appear on the right. So you can open it up and do it again, again. Right, so more precisely, so, mn minus 1 hats, I think I should have called it mn minus 2 hats, maybe. Yeah, probably. But generally, m hat of whatever is a product of at most that number of random swaps appearing on the right, and to the left you have a deterministic swap that appears there. That's fine, because you're only going to open the random swaps, and the induction is going to be according to the random number of random swaps that you have on the right. Now I know this is a bit unclear, so I took the liberty of actually doing a full example here for what happens when little n equals 3. Okay, so maybe let's do that. I think it will clear out some issues that you may not understand. Okay, so recall that M3 is the product of T1, T2, T3 for these choices, or not choices, for these T1, T2, T3. And let's start building the tree and see how it works. So first of all, at the top of the tree, you have M3, obviously. It corresponds to the uniform distribution. That's what you want, so you kind of build it that way. And as I said, at the root, there is no problem. So the left sum is going to be M2, which is T1, T2, right? And the right sum is going to be T1, T2, gamma 3, right? So the left sum takes this, and the right sum takes that. So that indeed the right sum is gamma times the whatever you sample from the left sum, and you get the convex combination that you want in terms of the parents, in terms of its children. So now if you continue down the tree on the left, it's actually simple. So the problem is when you go right, I mean, no problem, but you need to work harder a little bit. So now M2 is T1, T2. And again, and I also write the numbers here so that you'll follow up. These are the alphas. So the left is alpha and the right is 1 minus alpha. So going to the right from here, you get T1. And here what do you get? Well, you get T1 gamma 1 free. Why T1 gamma 1 free? Because you get T1 times gamma 1 free when you go right. You get T1 times I when you go left. Okay, so here you have a T1. And now, looking at here, let's get to a leaf. So when you are T1, you go with probability half to an I, with probability half to gamma I2. Gamma I2 is because T1 is composed of this gamma I2. And so this means that the leaf here is just the, do nothing permutation. And this is the 1-2 cycle swap. And okay, and that's that. Now, if we go back here, let's trace back here to this point, and we want to go right, then, it's T1 gamma 1 free, as we said, because of this gamma 1 free and this T1. But you want to write T1 gamma 1 free in a way that will be some product of matrices such that the random swap is on the right, so that you can keep on doing that. So let's see. So T1 gamma 1 free, well, I'm just kind of putting a gamma 1 free here, where inverse does nothing. And so that does nothing, but when I look at this thing, well, that is gamma 1 free, and this thing is T1 when you conjugate it with gamma 1 free. So what's gamma 1? What's T1? T1 is a random swap of 1 and 2, the probability half each. So when you conjugate it with 1 free, it really changes 1 to 3. So every time you see a 1 in T1, you should add a 3, you should put a 3. So really T1 conjugated by gamma 1 free is just probability half it's an I, and with probability half it's gamma 2 free. Right, so what we did here was to write this thing, which was the good way to write it when you consider its sibling, but it's not a great way of writing it when you want to continue down the tree. When you write it this thing, then you see what you need to take. So gamma 1, 3 is going to be the distribution on the left leaf here, and gamma 1, 3 times gamma 2, 3 is the distribution on the right. Right, so the gamma 1, 3 just kind of carries over. So, putting the numbers also and opening this up, you see that this leaf has distribution 1, 3, like not has the permutation 1, 3, and this has the sixth permutation 1, 3, 2, because that's what happens when you compose these two swaps. It's cleaned a little bit. Oh, maybe I overdid it. Okay. Good. So we are done with the entire left subtree of the root. Now let's move to the right subtree. So it's kind of the same, but up here it's kind of slightly more difficult because you do it twice. So right, M3 was the root, M2 was its left son, so M2 times gamma 1, 2 should be, which is kind of gamma 3 in our case. This is M2, and this is gamma 1, 2, which is the gamma 3, namely the gamma of T3, is what appears in here. And again, what I want to write it is not as a random swap, like T1, T2 times a swap. I wanted to write it in such a way that the random swap will appear to the right, so that I can open it up again. So let's do that. It's again the same thing. So I want to move this thing all the way here. So let's start by moving it. We'll do it all together. So I'm kind of putting both here and here gamma 1, 2, gamma 1, 2 inverse. See these two? And this has the effect of, if you bracket it differently like that, then of conjugating T1 and T2 to get the hats version. By the way, I don't write a hat version because T1 hat doesn't, it's not enough. T1 is being conjugated in different places in several different ways. For example, here by 1, 3, and here by 1, 2. So say T1 hat will cause you to forget the fact that it's kind of low, it depends on with who you conjugate T1 with. So in locally, it's nice to write it this way, but when you want to have a full picture, let's do it explicitly. So anyhow, T1 conjugated with gamma 1, 2 is just T1, because T1 is just this thing with gamma 1, 2, and I. So when you conjugate it, it stays the same. And T2 conjugated with gamma 1, 2, well, this is T2, and you switch 1 and 2, so you get, and here you have a 1 and 3 inside T2, so you get a 2 and a 3. Right, so what happens really is that this stays T1, and this becomes this thing. And that's great, because now that's a random swap to the right, so we can continue on. Namely, the left side of this vertex is going to get gamma 1 to T1 times I with probability 1/3. And the right side is going to get gamma 1 to T1 gamma T3. Okay, and from here it's kind of easy to go down. From here, the left side is going to gamma 1, 2. And to the right, you're going to get identity. So you see identity and 1, 2 appear several times. That's fine. They have to, there are only 6 permutations and 8 leaves. So in general, right, the number of permutations is little n factorial. And the height is the height of the tree is how many random swaps do you have, which is 2 to the n essentially, 2 to the n minus 1 minus 1, 2 to the n. And the number of leaves is then 2 to that, 2 to the 2 to the n. And so you're going to get a lot of repetitions because that's much larger than n factorial. That also kills any hope for getting an explicit construction like that, because it's a huge tree. Even the depth is exponential in n. So even if you can transverse it like that, it's going to take exponential time, or double exponential time if you don't know how to do it like per path. But there is a paper by Michael Cohen that solves this by considering a different tree. It's going to be a RATN tree, and its depth is going to be n. I'm not sure about the reality, but the depth is going to be n. So anyhow, that's one of the projects that you can choose. Okay, where are we? Yeah, so now we are here. So this vertex gets gamma 1 to T1, gamma 2 free, which again, using the same idea, kind of putting gamma 2 free inverse here, which changes nothing, but when you bracket it like that, what you get is gamma 1, 2, gamma 2 free, and then this thing, which is conjugating T1 by gamma 2 free gives you the same thing, but with 1 instead of 2. So you get gamma 1 free. And then so the left side gets gamma 1 to, so you look at this thing, the left side gets gamma 1 to gamma 2 free, which is 1, 2 free. It's not the same thing as that, by the way. And the right side gets gamma 1 to gamma 2 free, gamma 1 free, which is this cycle 2 free. Okay, and you can check that the probabilities are okay. So for example, what's the probability to get identity? So it's half times core times 1/3 times 1/2. So it should be 1/6, and here it's half of 1/6, but here you also have a half of 1/6. So you're fine. Also for the 1, 2, because they appear the same way. And the 2, 3, which appears only once, you see you get 1/6. And everything else is also 1/6. Okay. Good. I hope this example clarifies that maybe somewhat a little bit abstract recursion that you do in order to, or not recursion, the recursive construction of the distributions. Once you see it in an example, I think it's good. It gives some insights. Okay, so now we have the distributions over the vertices. What happens? What about the polynomials, right? So okay, so what do we know? So the distributions here are in red. So the distribution of the parent is the convex combination of the distributions of the two sons. And you know that the right distribution is the left distribution times gamma for some gamma. So what does it tell you about the polynomials? Well, the polynomials are just taking the expected characteristic polynomial according to the distribution. So the fact that the root is a convex combination of the two distributions means that the polynomial of the root is can be written like that, right? Which is great. And the fact that the distribution of the right son is gamma times the distribution of the left son, what does it tell us? Well, it tells us that you can write the polynomial corresponding to the right son, W, like that. That's obvious. But now, instead of writing it according to new W, you can write it according to new U, but you just need to replace the thing you sampled, P, by P times gamma because of that. So instead of P, I'm writing P times gamma, and here the transpose. Okay? Okay, so there are 3 things we want to prove about these polynomials. Let's see what we have. There's only one thing we don't have, and we'll prove. So the first thing that we have is that indeed for every V, PV is monic. That's, it's real-rooted? No, that's not clear. Keep deferring that, but that's going to be the last thing. So it's not going, it's still not clear it's real-rooted. At the leaves, it's real-rooted because these are just characteristic polynomials of some symmetric matrices. But expectations of those, I don't know. But it's still true that the degrees are all the same, degree n. So, for one, we got like, I don't know, maybe 50%, probably less. 0.2 is fine, right? 0.2, we wanted that the internal node, the polynomial attached to an internal node is a convex combination of the polynomials of the children. That's fine. That's this thing. And the third thing, which actually is going to imply what's missing in the fourth point, is that for every 2 siblings, the corresponding polynomials have a common interlace. Right? We need to prove that. So we need to prove that PU and PW, because of that, are going to have a common interlacing. But once we have that, we are also done with 1. right? We're going to do it like upwards. Why? Because if U and V have a common U and W, or PU and PW, have a common interlacing, and since PV is a convex combination of them, it means that it is also real-rooted. Right, this is lemma D. Let's go back to lemma D. Right, lemma D told you that if you have two polynomials, positive leading coefficient, everything is monic, everything is fine, and they have a common interlacing, that's what we are going to prove in point 3, then any point in the segment connecting them, and every polynomial that's a convex combination of them, is also real-rooted. And that's how we are going to establish the real-rootedness. You know, start with the leaves, everything there is real-rooted. We are going to prove that they have a common interlacing. And thus, their parent, which is a convex combination of these two polynomials, is real-rooted. And that's true for the parent of the, close by two other leaves. And then we continue from there onwards all the way up to the root, finally establishing that the expected characteristic polynomial according to the uniform distribution is real-rooted, as I owed you for quite some time. It was last week, but okay. Okay, so what we really want to prove is point 3, and then point 1 will follow. So we need to prove that the two polynomials PU and PW have a common interlacing, and that's a really neat proof. So let's say that. Okay, so the proof of point 3 is by induction on the height, but we need to strengthen the induction by proving that whatever we want to prove works for all symmetric matrices, not just the A and B that we are considering. So what do I mean? So we want to prove that point 3 holds. We are given A and B, we constructed this tree of distributions and polynomials, and we want to prove something about it. But what we are actually going to prove, and we use this as the induction, so we are going to strengthen the induction, is that for any A and B, what we are proving is true by induction on the height. Okay, not for our particular A and B. So for any A and B, every two siblings, the corresponding polynomial have a common interlacing. Of course, it's what you anyhow prove, because you prove it for every A and B. But I want to prove it, to use the fact that I'm proving it for every A and B in the inductions, because as you will see, one of the matrices B will change. So you will need to know that the theorem holds for any A and B, not just for the A and B that you have. It's a subtlety, but I think it's worth pointing it out. So let's see. So the base case, indeed, for every A and B, not just for our A and B, but it doesn't really matter here. P of a leaf is, a characteristic polynomial rather than expectation over those. And, the characteristic polynomial eats some symmetric matrix because A and B are symmetric. For every A and B symmetric, of course. And so this means that indeed this is real-rooted. I mean, we know that this is real-rooted. Here there's, the base case. So we want to prove real-rootedness and this property. So the real-rootedness holds there. Okay. And let's consider W, which is not a leaf. So PW, let's consider V, which is not a leaf. And let's look at its left and right sign, U and W. And let's consider W for the moment. So PW of X, we know that it relates to PU of X as follows, or to the distribution of U as follows. You sample P according to new U, and then you just conjugate what you get from the distribution, not conjugate, sorry, multiply by what you get from distribution by gamma. So this has the effect of conjugating B, right? But this is what it is. And if you remember lemma E told us that if you look at a matrix like that, so you conjugate B by a swap, that's the swap we got when you moved from the U distribution to the W distribution. But anyhow, if you conjugate by a swap, you can write this matrix, this new matrix as a, as a rank to update. So it's B minus U transpose plus VV transpose. Okay, so opening this up, you get the characteristic polynomial of A plus PB transpose. That's the B. And then you have minus PU U transpose P transpose, right? And then plus PV transpose P transpose. And now let's call this vector UP and this vector VP, just as a shorthand. So PW of X is really the expected characteristic polynomial when you sample according to U of A plus PBP transpose minus some, UP transpose plus VP transpose. Okay. Now we are going to define for every t the polynomial PT of X as follows. So it's going to be related, as you'll see in a second, to this polynomial. But okay, so let's see. So we are going to define it to be, again, we are sampling according to use distribution, and we are going to look at the characteristic polynomial of A plus PVP transpose, but plus TVPV transpose. Okay, so it's related to what we have here. Here we have the minus UP transpose, which doesn't appear, and we put a T here. Okay. So why am I writing that? Because if you remember lemma C told us that if you have, maybe let's go back and remind us, it was a long time ago. Right, if you have an n by n real symmetric matrix and you do a rank 1 update like that, but in that fashion with a parameter t, then the characteristic polynomial of this new matrix is the old one minus t times a polynomial of degree n minus 1, which also happens to be monic. Okay. So let's go there. Right, so I can write this polynomial per p as the characteristic polynomial of this matrix, A plus PBP transpose, minus t times some polynomial q, but I want to express the fact that q depends on VP, so I call it QVP of X. Okay, and that polynomial has degree n minus 1, or most time minus 1, but it's actually exactly minus 1, and it's monic. It's just a determinant of xi minus something. So, of size n minus 1. Good. So now opening up, like separating the expectations, what you get by this term is exactly PU of X, right? Because the expectation according to P sampled from gamma U, nu U of this thing is by definition PU of X. And then you have a minus T, because of the minus from the lemma C, times the expected polynomial of these QVPs according to P. I don't know much about those, but I know that this is an expectation of monic polynomials of degree n minus 1. So this is also monic of degree n minus 1. Good. And PU of X, I know, what do I know about it? I know it's real-rooted by induction on the height. Right, I'm proving real-rootedness. So I know it's real-rooted by induction on the height. Here there's no fancy thing going on. It's the induction with respect to the original A on the original B. So what I told you about the fact that you kind of generalize what you're proving is not, doesn't enter here. Good. So why did we do that? So let's look at PT of X again. And here, this is PT of X when we started developing it before. I kind of stopped here. So I think I stopped. Oh, where is PT of X? So, by its definition. So looking at the definition of PT of X, right, that's what the definition of PT of X. I mean, we did something with that. I'm kind of ignoring that now and looking back at the definition. PT of X is this thing, and now comes the cool part. So now what you do is let's open back VP to be PV trans. Let's open VP to be PV. So VP transpose is PV, V transpose P. transpose. And so doing that, you can see that you can write this polynomial as that polynomial. So A stays the same, but then P and P transpose surround B plus T VV transpose. And let's call this matrix B prime, this thing. It depends on T, but whatever. It's some symmetric matrix, regardless of what T is. And now, by the induction hypothesis, and again, now, and this is the point, now I'm using the induction on A and B prime, not on A and B. So that's why I need the proof to hold for every A and B. So by the induction hypothesis, PT of X is real rooted, right? Because U sits at a height in which I assume the induction holds, and A and B are maybe different than the original ones, but there is no original one. The proof is for every A and B. Good. And it's actually real-rooted for every T because, you know, the choice of T in R will just change the matrix B prime, but whatever choice you will make, this is a symmetric matrix, right? So it falls under the assumption that we have, and we know that it's real-rooted. And so this means by lemma B, so what's lemma B? Lemma B told us, it's here, that if you have a degree n polynomial P and a degree n minus 1 polynomial Q with positive leading coefficients, and you know that PT is always real-rooted for every T in R, then you know that P and Q interlace. Right? That's what that lemma said. And here we are in that situation. We define PT, this is PT, remember? And we just showed or used the induction to argue that PT is always real-rooted for every T. So that holds. So this means that P and Q interlace. P in our case is PU, right? It's like the thing that you get when you substitute T equals 0. It's this thing. So this means that PU and Q interlace. Good. So that's what we just had. And now from lemma A, what lemma 8 tells you, it tells you the other direction. It tells you that if two polynomials interlace and they should have the right degrees, so this degree n, this degree n minus 1, that's what we have, because Q is of degree n minus 1, the harmonic. So need positive leading coefficient, so the harmonic. So they tell you that if P and Q interlace, then I don't really care about that, I care about this thing, when P interlaces PT for any T larger than 0, right? And in particular for T equals 1, what this tells you is that PU of X interlaces P1 of X, right? Because let's just maybe, I don't know if it's clear. So we know that PU and Q interlace. And so we know that P, which is PU in our case, interlaces P of T for any T larger than 0. So let's take 1. So PU interlaces P1. And what's P1? Well, it's whatever, it's a weird thing, but it's whatever you get when you substitute T equals 1 to PT, and it happens to be this thing. It's something. Good. So let's recap. So what we just proved is that PU interlace P1. P1 is an unnatural, like in our case, polynomial. It's really, in a sense, it's a rank 1 update from PU. And now we are going to also show that it's a rank 1 update from PW, and therefore they have a common interlacing. But let's see. So by a similar argument, the same thing, but now you should, instead of defining PT, let's consider what's called PT hat. So it's also a kind of a weird polynomial, the expectation. Before in PT we had, you know, the matrix we care about, plus T VP transpose. Now we are going to take this matrix, and T is going to multiply UP transpose. And by the same argument, exact same argument, you can show that PW interlaces P1. Right, when you substitute 1, just as a sanity check, this and that goes away. So you indeed get this matrix, this polynomial P1. And when you substitute 0, you get PW of X, because you get the V please in a plus, this goes away, and and the minus UP transpose. So the bottom line is that PW and PU have a common interlacing, P1, which kind of sits in between in a sense, not in the segment sense, but as a rank 1 update between these two rank 2 difference matrices. And so they have a common interlacer. And that kind of means we are done. Because if they have a common interlacing, so we have this, and this means that their parent, the polynomial of their parent, which is a convex combination of them, is rooted, and that kind of bubbles up from the leaves all the way to the root, which finally established the proof of theorem 2, theorem 1, and everything. So as a recap, we proved in the last 2 weeks, which were actually 3 weeks in terms of content, but never mind, the R transform, finite R transform theorem, quadrature, and interlacing. And this is essentially finite tree probability. I mean, there are more papers on the subject, of course, but this is the basics. And with that, we are ready to go to the finite unit, which is going to essentially be a corollary, by the way, in which we're going to prove the existence of one-sided Ramanujan graphs of every size and every degree. And right, then we will sum up the course and